Our first topic in this course is going to be vectors. I assume you've all seen these previously, am I right? Maybe in applications in physics or in pre-calculus courses. But I'm going to start from the very beginning, as if you haven't seen them at all, but I'm not going to go that slow. I'm going to go through all the definitions and notions rather quickly. If there's anything I say that's not clear or that you want to clarify or ask about, just do it. Okay, never hesitate to ask. So, what is a vector? So a quantity in nature, any quantity that you take that has direction is denoted by a vector. So a vector is a mathematical object that's used to denote a quantity that has direction. For example, velocity. Velocity is a quantity. You can say I'm driving at 90. And that might be very, very fast if you're talking miles. It might be reasonable if you're talking kilometers. But it still has no meaning, or not a concrete meaning, unless you say where you're going. If you're driving 90 from Haifa to Tel Aviv, that's not the same as if you're driving 90 from Tel Aviv to Haifa. That's the opposite direction. Okay? So the velocity is something that has a direction. Can you give me other examples of natural entities that have direction that goes along with them? Right, force. Force has a direction. Okay, if somebody wants to come up here and have me push him, if I push this way or push that way, it will make a difference, right? Okay. A quantity that doesn't have a direction, okay, a quantity without direction is called what? Right, a scalar. Can you give me examples of some scalars? Right, mass is a scalar. There's no such thing as well, this is weight, but nevertheless, there's no such thing as I weigh 70 kilos north. Okay, or you weigh 255 kilos east, right? It doesn't have any meaning, okay? Can you give me other things that have a scalar as their time, right? Time is not a directional quantity, right? Somebody said speed, that's also correct, okay? So is it clear what the difference between a vector and a scalar is? Okay, and this is how we model things, and what we want to do is learn how to mathematically denote these things, how to be able to work with them, and there's a whole theory to go along, and there are two ways to relate to it. One is to start geometrically, and that's what we're going to do, and the other is to start from the algebraic point of view. We're going to start with the geometric point of view, define everything geometrically, and then we're going to see that it's the same thing as an algebraic point of view. We're going to see that they're the same thing. Okay, so if you've seen vectors written algebraically, like usually with coordinates, that's the algebraic point of view, and we're going to see that a bit later. Okay, so geometrically. Geometric definition. So here's a vector. We denote a vector by an arrow. That's a vector. An arrow has a direction, right? And it also has a certain length, okay, or magnitude. Okay, so arrows can go in different directions and can have different lengths. Do you agree? The way we symbolize it is usually we use Latin letters, small letters, and we usually put a small arrow above them. You'll see various ways to denote this. Sometimes it's written as A with a full arrow. Sometimes it's written A with kind of half an arrow. That's what I'm going to usually use. Sometimes you'll see very lazy people which just put a bar above it. And in textbooks, it's often written as kind of this very bold fat A. That I'm never going to use because that just takes a year to draw a single letter. Okay, so all of these are usually used to denote vectors. I'm going to use this normally. Okay, so that's how we denote a vector. So it's an arrow with a direction and a length. Okay, the length of a vector, length of a vector A is denoted by bars like this, very similar to the symbol for absolute value that you're used to. Okay, so this is the length of A. In this class, throughout the semester, we have to decide what is a unit, right, and what units we're measuring them. So our unit is going to be this marker, because that's easiest. So this vector is going to be 1, 2, this is about of length 3. Okay, you can of course measure in meters, in miles, in whatever. Okay, so that's the length of a vector. By the way, what kind of object is this? Right, it's a scalar. The length of a vector is a scalar. It's just a number. It doesn't have a direction. The direction is the vector itself. Do you agree? Okay. Now, when are two vectors the same? Okay, so for example, let's look at this black vector here, and let's look at this red vector here. I claim that they're the same vector. I can even call this one A. Why is that true? Because a vector, by definition, has two things. It has a direction, and it has a length. Okay, maybe we should write that. A vector has a direction and length. Those are the two things that comprise a vector. So if you take two arrows that have the same direction, I tried to have them have the same direction, and have the same length, then they're the same vector. Okay? It doesn't matter if they're rooted at the same point. Okay? So this vector, and this vector, and this vector, and this vector, and this vector, they're all the same vector. Okay? Clear? This is something that's not always consistent in various definitions. That's the way we're going to define it, and it's going to be important to many things we do throughout the course. Okay? So vectors do not see the point where they start. It's meaningless. All they have is direction and length. Okay. Some more notation. Maybe we can do it on this board. What about, let's look at this orange vector here. What about this vector? So this one has the same length as A in black or in red. Do you agree? But it doesn't have exactly the same direction. It has exactly the opposite direction. Okay? So a vector that has the opposite direction is denoted by minus A. Minus A is a vector that has exactly the same length as A, but exactly the opposite direction as A. Clear? I'm not writing everything that I'm saying, because that's just going to take very, very long. But if there's anything I'm saying that I said too fast, or you weren't paying enough attention, or you were still thinking about something else and you want to ask me, hey, say that again, do it. It goes like this. Hey, say that again. Okay? Okay, so that's what we denote by minus A. the magnitude of a vector, or the length of a vector, it's always a positive number, right? It's the length of a vector, but it can also be 0, okay? So now we're moving to a new board. 0 with an arrow above it is the 0 vector. It's not the 0 scalar. It's not the same thing. It's the 0 vector. It has length 0, obviously, but it doesn't have a direction. The direction is not well defined, okay? And in particular, I can't really draw it, okay? So this is called the 0 vector. A vector of length 1, so this is the 0 vector, is called, do you know? Right, a unit vector. How many of these are there? I'm going to stand here and wait until you answer. How many unit vectors are there? Right, infinitely many. In any given direction, you can take a vector of length 1. Do you agree? Okay, so there are infinitely many unit vectors. It's not the unit vector. It's a unit vector in any given direction. Clear? And the way we denote unit vectors is called a unit vector, denoted instead of this regular arrow, it's denoted with a little hat like this. So this is how we denote a unit vector. Okay? How do we add vectors? Addition. So since everything is defined geometrically, everything is defined in terms of these pictures, I'm going to define addition just the same way. So here's a vector, let's say A. Here it is. This is A. And here's another vector, let's say B. Here it is. This is B. And I want to add A and B. So the first thing I do, I draw B so that it starts where A ends. So here's B again. And note that the way we defined it, this is not a vector of the same length of B, or a different vector that represents B, or any way of saying it. This is B. It's just the same vector. Do you agree? Because it has the same direction and the same length. So this is B. Okay? But now that I drew them like this, I can define A plus B to be a vector that starts where A starts and ends where B ends. So this is the vector A plus B. By definition, that's how I define addition of vectors. Clear? Everybody? Okay. Once in a while, please do me a big, big, big favor and do this. So I know that you're with me. Okay, I know it's hard work, it takes a lot of effort, but I would greatly appreciate it. Okay? Thank you, thank you, thank you. Okay. Question. Suppose we know the length of A and we know the length of B. What can we say about the length of A plus B in terms of the lengths of A and B? Answer. Have you ever seen the law of cosines? You've seen it. So let me remind you. So it says the following. In general, if you have a triangle, let's draw a triangle. And this is a completely general triangle, not necessarily a right triangle. And let's call this A, and this B, and this C. These are just the lengths of the edges now. Okay. And the law of cosines says the following. This is a theorem in trigonometry. It can be proved using tools of trigonometry. let's call the angle opposite from C, let's call it alpha. And it says that C squared equals A squared plus B squared. Let me stop here for a second. If alpha is 90 degrees, this is it, right? And this has a different name. It's called the Pythagoras theorem, right? But if alpha is not 90 degrees, this is no longer true. This is only true if alpha is 90 degrees. There's another factor that comes in, and the factor is minus 2 times AB cosine of alpha, and that's why it's called the law of cosines. Note that if alpha is 90 degrees, then cosine of alpha is 0, and therefore this entire term disappears. Okay, so this is the law of cosines. Now we can take this and deduce from it what is the length of A plus B in this picture. Let's go back to this board a second. This is a triangle. Let's call this angle between A and B, let's call it alpha. And now we know that the length of A plus B, equals, if I square it, it's going to be this square plus this square minus 2 times and so on. So I'm going to take a root. So it's the root of the length of A squared plus the length of B squared minus 2 times the length of A times the length of B times cosine this angle alpha in between them. And now I just have to somehow manage to make a straight line, which is this root here. Do you agree? So this is precisely the law of cosines for this little picture. Clear? Questions? Everybody good? Okay. Now, I have an important remark at this point, and you're going to see why it's important only later. Usually, when we talk about angles between vectors, usually we're not going to mean this angle. Okay? Usually, so let me write it here as a remark. In most cases, alpha, the angle between the vectors, is going to be the angle between them when we draw them starting at the same point. So if this is A and this is B, this is the angle we're going to call alpha. In most of the instances where we're going to discuss an angle between vectors, in various contexts, it's going to be this angle. And the different one is actually the one we already discussed, which is when we talk about addition of vectors and we want to know the length of the sum, then alpha is not the angle between the vectors when we draw them starting from the same point, but rather, back to this board, when we talk about addition, the alpha in the formula is the angle between the vectors where one starts where the other one ends. Okay, clear? So this is a little delicate thing to pay attention to, that's all. Okay, so when you say angle between vectors, usually you don't mean this one, you mean the other one. Okay, clear? Okay, good. How do we subtract vectors? So let's clear ourselves some more space. How do we subtract vectors? So the answer is we're going to use this notion of minus A, of a vector pointing in the other direction. So by definition, A minus B is going to be defined by definition to be, you take A we know, you add, to add we know, we just defined how we add vectors, but what you add to it is minus B. And minus B we also know, it's a vector in the same, in the opposite direction of B of the same magnitude. Is it clear? So this is how we define subtraction. Okay, so for example, if this is A, and let's say this is B, this is B, so what's A minus B? I take A and I add to it minus B. Minus B is a vector pointing in the opposite direction of B of the same magnitude. This is minus B. Do you agree? And I add A to minus B, and what I get is this vector here. So this is A minus B. Clear, everybody? Okay, good. Another important notion is multiplying a vector by a scalar. Okay, so for example, multiplying, this word multiplying, let's call it product. Okay, product. The word multiplier, the word product, when you talk about vectors, is very tricky because there are like 4 or 5 different notions of product for vectors. Okay, so we're going to have to be careful. So product of scalar times vector. You can't get around it using the word times or using the word multiply or using the word product. It's always going to be not well defined unless you state explicitly what you mean. So what's the product of a scalar times a vector? Okay, so let's say our scalar is going to be little m and our vector is going to be A. So what is MA? So let's look at a picture first. So what is this thing? Suppose I take B and take B again and B again. Okay, so this entire thing is going to be 3B. This is the vector 3B. That's M is 3 and B. Is it clear? Okay, so what is 1/2 B? It's going to be a vector in the same direction of B, but 1/2 the length. Okay, and what is minus 2B? So it's going to be a vector whose length is 2 times the length of B, but the direction is the direction of minus B, the opposite direction. Clear? Okay, so here's the more formal definition. MA, maybe I'll do it like this. If M equals 0, then M times a vector is the 0 vector. If I take 0 times a vector, I get the 0 vector. Clear? If M is positive, then M times A has the direction of A and length M times the length of A. Is it clear what I wrote? So if M is positive, example 3, anytime you're thinking of something abstract and you're having a little trouble to, wait, this is too abstract for me, you always think of examples of concrete numbers, right? So if M is 3, 3 times a vector is a vector in the same direction of A, but length 3 times the length of A. Clear? What if M is negative? If M is negative, then MA has the direction of what? What's the direction of minus 3A? Right, it's the opposite direction, so it's the direction of minus A. And what is its length? And length Do you think I can fit 3 more rows here? Well, it's only one way to know, to try. And length, no, we're almost done. And length what? What's the length? Can I say that the length is MA? M times the length of A? Not exactly. If M is minus 3, the length can't be negative, right? So the length is going to be absolute value of M 3 times the length of A. Can everybody see this down here? Okay. Clear? So if I take, let's do an example. What is the, suppose M is negative 3, then negative 3b is going to be a vector in the opposite direction of b, whose length is 3 times the length of b, right? Not minus 3 times the length of b, 3 times the length of b. So this is minus 3b. Direction opposite to b, length 3 times the length of b. Clear? So is it clear why I wrote here m in absolute value? Okay. One thing to be careful about is that we're using here, we're often doing what's called abusive notation. We're using the same notations to denote different things. Okay, and you have to be careful. So this absolute value sign here around A is the length of a vector, whereas this absolute value sign around M is the absolute value of M. Okay, those are 2 different things. They're related, we're going to talk about it, but they're 2 different things a priori. Clear? Questions? Okay. Many times, given a vector, we're going to want to know what the unit vector in that direction is. And that has a name, it's called normalizing a vector. So, normalizing a vector is just finding a unit vector in the direction of a given vector. So suppose I have a vector A, and I want to find a unit vector that has exactly that direction. How do I do it? So here it is. A with the little hat is going to be the unit vector. That's how we denote unit vectors. And what is it going to be? I'm going to take A, and what I want to do is, let's think for a minute. Suppose A is of length 3. How do I find a unit vector in the direction of A? I have to multiply A by the scalar 1/3. Right? I have to take 1/3 of A. If A was of length 3, 1/3 of A is going to be of length 1. Do you agree? Okay. If A was of length pi, how do I find a unit vector in the same direction? I have to multiply it by 1/pi. Do you agree? In general, I want to multiply A by the scalar 1/the length of A. This is a scalar, this is a vector. I know how to multiply vectors by scalars. That's what we just defined there. Okay? And this is a unit vector. Okay? Because if this was of length 5, now I'm taking 1/5 of it. It's of length 1. Clear? Everybody good? So this is called normalizing a vector. And so this notation. And some rules. Rules is a very tricky word in mathematics. There's no such thing as rules. Okay? This is not religion, and it's not a country, it's math. In math, there are 2 things. There are definitions. Okay? You can define anything you want in the world. Okay? Usually it will have a life and survive if it's a useful definition, if there are things that can be done with it. If you define something that's useless, usually it would disappear in history. Okay? And then there are theorems. Theorems are based on the definitions and always require proof, rigorous proof. Okay? We're of course not going to be able to prove everything that we do. Many times we're not going to prove things because they're kind of standard or too easy or good as exercises, and we don't want to actually prove everything we're doing. That's rather tedious and boring. Sometimes we're not going to prove things because they're too hard. The proofs are too difficult and tricky, and sometimes proofs are very, 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 very amazing. Amazing compared to the simplicity of the statement. Sometimes a very naive statement could have a very, very hard proof. Okay? So when I write rules, it's not something that I give, hey, these are the rules. No, it's a theorem that requires proof. Okay? Always. So rules. So here's rule number 1. A plus B equals B plus A. Let's erase this. So what do you mean A plus B equals B plus A? That's obvious, right? Addition always satisfies this. No. We just defined a totally new addition. It's addition of some geometric objects. You take one, you draw it where the other ends, you take the line that starts where the first one starts and ends where... This is a totally new concept, right? Why would this be true? Just because when we wrote plus for numbers it was true? Or because when we write plus for matrices it's true? No. You have to prove it. Okay? How do you prove something like this? You take two vectors, in general, okay? Draw A and then B, draw B and then A, and see that you get the same thing. Okay? This one's very easy. I'm just going to very quickly draw it for you. So if this is A and this is B, right? Then what you get as the sum is this thing. Do you agree? And if you were to draw first B, let me draw B here, and then A, the sum would be the same thing. Do you agree? So this is a proof. This is a geometric proof of this statement. Okay? I'm not going to do all these proofs because you can see they're kind of little tiny exercises, but you have to do them or at least run them through your head to see that you agree. Okay? And in particular, we're going to see many, many notions, even today, that are not going to obey all the regular things that you believe. So we're going to see a different product a bit later today that is not going to satisfy everything you know about products. Okay? So you always have to be careful with new notions. Okay, so this is the first rule. Okay, it's a theorem. It says, how do you say it in words? It says that addition of vectors is commutative. Okay, clear? Okay, rule number 2. Addition of vectors is associative. A plus B plus C is the same as A plus B plus C. Try drawing the proof for it. It's really easy, but try to see that you know what you're doing. Okay, try it. It's a very good exercise. So this is associativity for addition. Another one. If you take a scalar m and multiply it by n times a, okay, so note that scalar multiplication we're writing without no little crosses or dots or anything, and that's important because those are going to have different meanings for different kinds of products. Okay, so this is the same as multiplying the scalars. This is good old multiplication in R of numbers, and then taking this scalar and multiplying it by the vector a. Okay, this requires proof. And the proof is going to be geometric because everything we defined was geometric. Do it. Okay. Here's another one. If you take two scalars and add them and then multiply by a, then this operation is what's called distributive. Okay, it's the same as m times a plus n times a. Okay. Make a little picture, make sure that it makes sense, and that you agree with this. And here's another one. If you take a scalar, m, and multiply it by a plus b, again, this is going to be a totally different form of distributivity. Okay? Here, this plus and this plus are totally different things. This is addition of vectors, and this is addition of numbers. Right? Do you see that these two things, although they look the same to me, but they're different things? Do you see that? Okay, so this is MA plus MB. Okay, so two forms of distributivity. Questions? Everybody good? Okay. Good. Now just another bit of terminology that we want to pick up. So two vectors that have the same direction, but not necessarily the same length, so they're not the same vector, okay? But since they have the same direction, you can think of them as lying on the same line, okay? And the word for this is colinear. That's what they're called. So let's write that definition. Two vectors that have the same direction are called colinear. Colinear vectors. Okay? Now, how do we identify them? How do we know the two vectors are colinear? What do they have to satisfy? So if they have the same direction, we can express one as a scalar multiple of the other, right? If this is A, then a vector in the same direction is going to be maybe 3 times A, or 1/3 times A, or 5 times A, 7 times A, 9 times A. Clear? Okay, I'm waiting for you guys to say this, or otherwise I can multiply vectors by lots of numbers and it's fun. Okay, so they satisfy that A equals sum M times B. Okay, where M is non-zero. That's important. Clear? Okay, and this is a matter of agreement, so we're going to call two vectors colinear even if they have opposite directions, so even if this M is negative. Okay, as long as they're on the same line, we're going to call them colinear. Okay? Okay, this notion of colinear vectors is something that when you learn, if you've already learned it, or when you learn it in algebra, this is what's called in algebra being linearly dependent. Okay, I don't know if you've met this, you haven't learned it yet. Okay, so in algebra, vectors are called linearly dependent if one is a scalar multiple of the other. Okay? Okay, so yeah, so we're gonna stop this lecture here, and in the next one, what I want to discuss is the algebraic point of view on vectors. Okay, so namely, I'm going to take these geometric objects, which were floating there in space, and we know how to add them and subtract them and multiply them by scalars. I want to somehow force them into good old Cartesian axes, right? X, Y, and Z, and somehow express them in this coordinate system and be able to do these operations of addition and subtraction and multiplying by a scalar when they're given as coordinates. Okay? That's going to be the next movie. This is also going to be our